Assuming normally distributed data, which thanks to the central limit theorem we can often assume, a z-score, or it pains me to say this, a z-score, which I grew up Canadian, and so we typically say z, not z, but in statistics, this really is what people call a z-score. So I'm generally going to be calling something like this z, but in the context of the z-score, I mean, I've just got to call it a z-score. So a z-score indicates how many standard deviations away from the mean a data point is. So for any given data point xi, we can get its z-score by subtracting the mean of the distribution from that individual point and then dividing by the standard deviation. So this z-score formula, this is really the same as what I had on the board, except I'm using mu here, which you might remember from earlier in these live lessons, is typically used to symbolize a population mean, where we have all of the data, and x bar is used where it's a sample mean. But either way, we're talking about the mean of the distribution. So this formula standardizes a given score, xi, a given value, to the standard normal z distribution, right? So I just referred to the standard normal distribution as the z distribution, just in the preceding video. So let's see an example of z-scores in action. Let's say that, for example, you get 85% on a CS 101 exam, so an introductory computer science course, and that sounds like a pretty good score. And you did do extremely well relative to your peers, to your classmates, if the mean was 60% with a standard deviation of 10%. So here are the values. So here's your 85%, xi, and then we have a mean of 60%, mu, and a standard deviation of 10. So we can sample from a distribution with those characteristics. Let's say you're in a big class. This is like a massively online course or something. There's 10,000 students in the course. And let's plot out the distribution. Nice, here it is. So here is how your 10,000 peers did. This is how you and all the students in the CS 101 course did. So we have a mean of 60 and a standard deviation of 10. So you, in purple here, you got 85. And so you are 2.5 standard deviations above the mean. So each of these olive green lines indicates another standard deviation. So you are 1, 2.5 standard deviations above the mean with your score of 85. So the vast majority of your classmates, everyone down here, this big clump of the distribution, they scored worse than you. There were very few people up here who scored better than you. So yeah, your z-score is 2.5 standard deviations above the mean, and we can calculate that using our formula here. So your score minus mu divided by the standard deviation. We've got that here. Your score minus mu divided by standard deviation gives us a z of 2.5, a z of 2.5. Man, that's tricky for me. All right, so using our simulated class of 10,000 CS 101 students, we can get a very similar result. So instead of using the population mean mu and the population standard deviation, which, so we use those, remember, as inputs to our sampling, to our sampled distribution here. So these are supposed to imply some real underlying truth about the entire population of all the CS 101 students ever in the history of time. I don't know what the population really is, but we have a sample of 10,000 CS 101 students, and so we can calculate what the mean is in our sample distribution, and we can calculate what the standard deviation is using NumPy methods in both cases for the mean and standard deviation respectively, and doing that on our pretty big sample of 10,000 students. we get the same score, 2.5. So what does this mean? It means that less than 1% of the class outperformed you. So of the 10,000 people in class, there's only a very small number up here, 69 people who had a z-score higher than 85, who had a score higher than 85. So that corresponds to just 0.69%. So less than 1% of the class outperformed you. And using some of the terminology from earlier in these live lessons, the idea of percentiles, the 99th percentile falls at 83.3. So at 83.3 here, that's the 99th percentile mark. So only 1% of students scored above that, and you are in that top 1%. All right, so now that I have you feeling really good about your performance on that CS 101 test, that 85 that you got, let's consider another scenario. So in this scenario, the mean score of your classmates is 90, and the standard deviation is 2. So in that case, let's sample 10,000 data points from that population and have a look at what it looks like. So now, the average score is 90, and the standard deviation is much tighter. So your performance of 85, now not looking so hot. Now you're right at the bottom of the class. So your z-score now is 2.5 standard deviations below the mean. So with our mean being here, you're 1, 2, 2.5 standard deviations below the mean with that score of 85. And so, using our simulated 10,000 data points, we get, very close to that negative 2.5, very similar to what we got with the population level metrics that we used to seed our sample distribution. And in that case, it means that over 99% of the class outperformed you because 9,933 of the 10,000 students got a score better than your 85. And so, 99.33% of the class did better than you. Only 67 people did worse. And so this means that you're now in the first percentile. You're in the bottom 1%. So the threshold now for the bottom percentile is at 85.37, and you scored 85. So you are in the bottom 1%. So other than making you feel really good or really bad about your performance on this hypothetical CS 101 test, z-scores come in handy all over the shop. We're going to be making use of z-scores or z-scores quite a bit in these live lessons, but right off the bat, let's talk about outliers. So it's a convention in frequentist statistics to consider a data point that lies further than 3 standard deviations from the mean to be an outlier. So more than 3 standard deviations from the mean, we consider that to be an outlier. So you scored 2.5 standard deviations from the mean in both of the scenarios that we ran. And so that was not considered an outlier. But data points that are more than 3 standard deviations above the mean or more than 3 standard deviations below the mean, we might consider those to be outliers. They might be related to something odd going on in your data collection, or maybe mislabeling a data point, a wrong data point. So it's a good idea to individually investigate outliers in your data, as they may represent an erroneous data point. Just some kind of error in your process, a failed experiment, a data entry error, or so on. And so you should consider that outlier perhaps for removal from further analysis, especially because outliers can have an outsized impact on statistics, including mean and correlation. It may even, by looking for these outliers, it may tip you off to a major issue with your data collection methodology or with your machine learning model that can be resolved or that you can come up with a unit test for to look for in your production code.